Thanks for the invitation. And this is also a meetup of the New York Physics and Astronomy meetup group and the Clean Energy group. So welcome to all. So clearly, if anybody has been following this field at all, they're aware of that there is a crisis in cosmology. And this has been reported over the past 2 years in a number of different publications. And as the introduction sort of gave away, the question is, what is the cause of the crisis in cosmology? And in the first part of this presentation, I'm going to be presenting the reasons why this crisis is being caused by a failure of the basic paradigm of current cosmology, which is the Big Bang hypothesis. The only way out of this crisis is to recognize, as I wrote 30 years ago, that the Big Bang never happened. So after this first part of the presentation, we'll have a brief break for questions, and then we'll go on to the second and third parts of the presentation, where I'm going to be presenting, if the Big Bang never happened, what did happen in cosmic evolution? And finally, what difference does it make? And especially, what difference does it make to the effort to develop fusion energy? And then we'll have a longer period of question and answer. So to begin with, the problems of the Big Bang hypothesis go way beyond what is generally discussed as the crisis in cosmology. And this is starting to be recognized by many researchers. Perhaps the most fundamental predictions of the Big Bang hypothesis derive from the idea that the universe started at a highly hot and dense period as a completely homogeneous and isotropic cosmos. From that, we can derive the idea that in the theory, large-scale structures, galaxies, clusters of galaxies, so on, derived by the gravitational collapse of initially very tiny irregularities in this hot plasma. Since the Big Bang hypothesis says the universe formed 13.8 billion years ago, if we look out into the universe and see the velocity at which objects are moving in the universe today, we can mathematically derive what the biggest objects in the universe are. And we're freezing again. What we found, what everybody has agreed to, is that those biggest objects should be no larger than 1 billion light years. Now, 1 billion light years certainly sounds like a fairly big distance, but if we look out into space, as our telescopes got more and more powerful, we saw greater and greater conglomerations of matter. It's interesting historically to say that back in the 1930s, when this hypothesis first was put forward, there was no evidence that at the largest scales, the universe was homogeneous, and therefore there were no large objects beyond 1 billion light years. And as the evidence accumulated, we didn't see any evidence of this convergence to 1 billion light years. Now, it isn't just me saying that 1 billion light years is the limit. Even such pioneers of the Big Bang as Joseph Silk said back in '88, if you saw large objects extending over 1,000 megaparsecs, that's 3 billion light years, you would have to question the Big Bang theory. Well, what has happened now is that we have seen the discovery over the past decade of many objects that exceed this limit. Just to start with the most recent example, at the last American Astronomical Society meeting, Alexis Lopez demonstrated the discovery of a 3 billion light year arc of galaxies, an arc so big that in the sky it extends about 15 degrees, 30 times the diameter of the full moon. But this discovery is only the most recent of a chain that have been published in the peer-reviewed literature. For example, the Cosmos satellite, which was looking, the Cosmos survey, which was looking at a very small part of the sky, but looking very deeply out into space and back into time, discovered conglomerations of galaxies that stretched over many gigaparsecs, so 3 to 6 billion light years. And this graph shows the concentration of galaxies as you go out into redshift, showing major differences in density over extremely large distances. Other surveys of, for example, gamma ray bursters, which can be seen at great distances, show that they too have concentrations in the sky that cannot be explained as statistical variations and extend over billions of parsecs. So all of this data presents a severe challenge to the idea that there was a Big Bang, because we can flip the equation and say, how long did it take, at a minimum, to form these structures? And it must have taken at least 100 billion years. So this is a major challenge in the sense that the clear predictions of the theory are contradicted by multiple data sets. Now, there's a second very important, but not too publicized prediction of the Big Bang. Obviously, the Big Bang assumes that the universe is expanding, that the explanation for the well-known observed Hubble relationship between the shift to the red of light from distant objects and their distance, the explanation for this observed phenomena is that the universe is expanding. Now, there are some direct geometric consequences of the idea that the universe is expanding, and that's the reason for the Hubble relationship. The most important of these is what's called surface brightness dimming. Now, the surface brightness of an object is easy to explain. If you take the apparent luminosity of an object on the sky and you divide it by its apparent area on the sky, that's its surface brightness. If you have ordinary space, which is not expanding, and you move an object like a lamp twice as far away, its apparent area will contract by 2 squared, 4, and its apparent luminosity will go down by 2 squared, 4. Therefore, the ratio of those two numbers, the surface brightness, will be a constant independent of distance. So the surface brightness of an object in non-expanding space is independent of its distance. But in expanding space, this object was closer to us when the light was emitted, and therefore it looks larger. So its apparent area on the sky is increased, and its apparent luminosity is decreased because as time is stretched, there are fewer photons arriving per unit time. The net result is that in an expanding universe, the surface brightness of objects goes down as the quantity 1 plus z cubed. Well, my colleagues and I, Dr. Riccardo Scarpa and Dr. Renato Fulamo, have for many years studied this and published our results in peer-reviewed journals, looking at what is the actual surface brightness of galaxies. And we find that the surface brightness data is an excellent fit to no expansion. So this plots redshift versus the logarithm of the surface brightness of galaxies. So this is a factor of 10, a factor of 100, a factor of 1,000. The red line is the Big Bang prediction. And these dots of various colors are dozens or hundreds or even thousands of measurements of actual galaxies going out into space by the Hubble telescope and other telescopes. And what we find is that the slope is insignificant. So there's an excellent fit to the zero evolution of no expansion. For equal luminosity, the galaxy's apparent radius would be constant to 1%. So this is a tremendous contradiction to the very idea that an expansion is occurring. And this has been published in the biggest journals. And there are counter arguments where people say, well, the explanation is the galaxies were really, really tiny, and this completely nicely compensates for the expected surface brightness dimming. And in the question period, we can get into why that can't possibly be the case. But this is, again, a fundamental contradiction of the very idea that the universe is expanding. Well, what people have been mainly hearing about in the crisis of cosmology coverage is the contradictions that arise from the study of the cosmic microwave background. Now, the cosmic microwave background, this very dim radio glow throughout the universe, has been cited as a key proof that the universe was once billions of degrees hot, even though the actual observed temperature is 2.7 K. So this is quite an extrapolation by a factor of trillions and trillions. But the theory makes certain concrete predictions that really can't be changed about the very small fluctuations that occur in the brightness of the cosmic microwave background as you look at various points in the sky. And if you look at various points in the sky, you find that in contrast to these predictions that the fluctuation should be random or Gaussian and isotropic, the same all across the sky, they're not. So this is a map based on the observations by the Planck satellite of very small fluctuations. This is of the order of tens of microkelvin across the sky. And the red areas are slightly hotter, slightly more intense. The blue areas are slightly colder, less intense. Well, you can see by these large-scale fluctuations, or large scale on the sky, that they aren't random. The fluctuations actually lie almost in a plane. And they aren't isotropic, because if you look at the fluctuations on the left-hand side of the drawing, they're much smaller than on the right-hand side. Now, this seems to align either perpendicular to the ecliptic, which is the curved line, that's the plane of our solar system, or is almost parallel to the plane of our galaxy. Now, that shouldn't be happening at all, because of course, in the Big Bang theory, this radiation is coming from billions of light years, far from our solar system or our galaxy. But there are many individual ways of measuring this that all add up to the fact that this is not random, this is not isotropic, and this is not in accord with the predictions. Now, there is one exception to these predictions, that on the very largest scales, there should actually be correlations. So there's a very interesting prediction because it's quite concrete. So the Big Bang theory, as modified by inflation, dark matter and dark energy, predicts that the correlation of intensities on the sky, of course, will be very high when the distance between the 2 points being correlated is low. That's to be expected. But what isn't expected is that this theory predicts that there should be negative correlations at about 60 degrees apart on the sky and positive correlations at 180 degrees. So there should be more than random correlation when you look at opposite sides of the sky. Well, the blue line is Planck's observations of these correlations. And what you can see easily by eye, and it's confirmed statistically, is that the correlations that are predicted just don't exist. And I took the same data and I divided the predicted, the observed amount of correlation by the predicted level. So the predicted level is unity. And this is the actual observed correlation. And you see, except for the areas where both curves cross the axis, and of course their ratio becomes not significant, the correlations are much lower, about a factor of 5 lower than predicted, and are quite in accord with no correlation whatsoever. So these are fundamental contradictions of the quantitative predictions about the cosmic microwave background itself. But there are other contradictions. So if we look at the precise measurements that have been made by the Planck satellite of the degree of correlation at various scales, the degree of fluctuation, excuse me, at various scales on the sky, this is a plot of how much amplitude of fluctuations there are at various scales. And this is measured in spherical modes. So the more the spherical modes down here, that means the greater number of pieces you're dividing up into the sky and see how much fluctuation there is at smaller and smaller scales. So the blue dots are observations. Now the present theory has 9 fitting parameters or free variables that cosmologists can use to make a nice fit to this curve. So in this right-hand part of the curve, you do have a very nice fit, but then again, you have 9 free variables to make that fit. When you get to the larger areas, you sort of have this embarrassing dip where there isn't much of a fit at all. But the most interesting thing is these free parameters that cosmologists use to fit this curve make predictions about other data sets in the universe. So these free parameters are things like the Hubble constant. So you fit the Hubble constant to this curve, you get a prediction of what the Hubble constant is. What is the relationship between redshift and distance? Well, of course, that can be measured by actual observation. And the measurements based on supernova and other data points over the past 20 years have pretty much nicely converged in this upper curve and have converged around 72 kilometers per second per megaparsec, which is the units they use. But the problem with the predictions is they started out being pretty close to observation. And as the observations of the microwave background got better with Planck, the predictions diverged. This is what people call the crisis in cosmology, because of course, there's a prediction that is now wrong by approximately 5 sigma, by a very big margin. So that's in addition to all of the other contradictions I've outlined. Another big parameter that is predicted by this fit is the density of the universe in ordinary matter, baryonic density. Now, why is that important? Well, since the Big Bang predicts that the universe started with a hot, dense conglomeration of matter, that necessarily produced fusion reactions. So you necessarily produced certain amounts of light elements, helium, deuterium, lithium. And the amount is determined by the density of the universe at the present time. So you can predict, and people do predict, the amount of helium, deuterium, and lithium. Well, for deuterium, gee, there was good news for the Big Bang theory, because this is the one data set that the theory fits very well. It does accurately predict the amount of deuterium, the heavy isotope of hydrogen, observed in the universe. But for the other two predictions, helium and lithium, it's way off. So the prediction for helium is 24%. So there should be stars and galaxies that have more than 24% helium, because helium is produced by fusion reactions in stars, but there should be none that is less. Well, if we look at stars that are close to us, what we find is that lots of these stars have helium abundance that is far less than the predictions, which is the red line. You have helium abundances down to 11%, even down to 5%. And this has been known for at least 10 years. In the case of lithium, the situation is even worse, and this is known as the lithium problem. Lithium abundances decrease towards zero as we look at stars that have less and less iron and other materials, elements that we know are made by stars. So as we look at more and more pristine stars, the level of lithium drops to about 1/20th, or compatible with zero, compared with the predictions of the Big Bang, which are up here with those red lines. So again, very fundamental prediction that can't really be altered, and complete disagreement with the observations. I don't have time to give a comprehensive list, but if you just look at some of the most prominent ones that have developed over the past 20 years, and especially over the past 5 years, you have all these disagreements between predictions and observations, just dealing with the CMB. And the chances of these being random, due to a small sample of data, 5 in a million, 3 in 10,000, 3 in 10,000, these are almost impossible to be due to chance. If you add them up, all up, of course, by multiplying the chances, these are independent data, it becomes impossible that these are due to random variations in the data. So right now, we have the situation in 2021 that the Big Bang hypothesis predictions are in conflict with observations of 16 independent data sets and are in agreement with only one, the one I mentioned, deuterium abundance. Now, this isn't just me speaking. If you look at the published peer review literature, you have people pointing out these individual discrepancies over and over again. For example, recent publication in Nature Astronomy, a prominent publication, these inconsistencies between disparate observations show that the flat lambda CDM, so that's the dark energy, dark matter model, the current model of the Big Bang, do not seem to any longer provide a good candidate for a concordance cosmology. Another set of observers say, here we have argued the Hubble tension could be another manifestation, yet another manifestation of the breakdown of the FLRW model. Well, what is that? That's the Friedmann-Lemaitre-Robertson-Walker model. It's a scientific name for the expanding universe Big Bang model. So, does that mean that other people or anyone is saying in peer-reviewed, published journals, as I did 30 years ago, that the Big Bang never happened? Well, the answer is no. Actually, nobody is saying that, not even me. I haven't said it in a published peer-reviewed publication since 2003. And the reason is, and I have had this on high authority in writing, that leading journals on policy will not publish any argument that the Big Bang never happened. They will publish various contradictions with various parts of the theory, but they will not publish an overall survey. Now, we can get in the question period of why this is the case, but at the moment, the situation can be described by what I call the ENC effect. So the ENC effect is the emperor's new clothes effect. So it's like you can say, I see the emperor's elbow, I see the emperor's knee, or even I can see the emperor's rear end. But you cannot say in a published peer-reviewed journal, that's because the emperor's wearing no clothes. Because if you do say that, you're either stupid or unfit for your job. So that's the situation today. We're not in a published peer-reviewed journal. So I can tell you today, the Big Bang theory is wearing no clothes, and the Big Bang did not happen. So let's break here for 5 minutes, and I'll take a few questions, and then we'll get into what did happen. So don't ask me questions about what did happen. We'll get into that shortly, but I'll take a few questions about what I've presented so far.
I also have a chat line. You can put your question in there and I will read it. Okay, if you can go into the chat line, there's Mike. It says, can you in the question answer why those who control the published peer review think they're still doing science?
Well, I think that it's a complex sociological problem that has happened over the years. But basically, you have a field in which the funding is controlled very centrally. You don't have a lot of funding sources for cosmology. They're basically, it's funded by a few government agencies in most countries, like our NASA and our National Science Foundation. So when you have centralized funding, you have the possibility for orthodoxies developing. Orthodoxy developed where basically the people who are allocating the money are theoreticians who have spent their entire lifetimes developing these theories. And as is natural, they're human beings. They don't want to see these theories contradicted. This spreads to a wider circle because there's basically an alliance between media journalists who think this is a great story. It's a wow, gee whiz story, dark energy, dark matter, things we don't understand, and the people who control the funding. So the net result is you have an overall climate where even people who aren't dependent on funding, and most of these big publications are private publications, they fear their reputation. They fear the overall concordance, as it's called, bureaucracy will attack them if they break with that. And that's the fear that's sort of holding back the field. So even though individual contradictions are being published, the overall paradigm change, which is necessary, is being held back.
Okay, we're getting quite a few questions here. Can you see the chat line, or do you just want me to keep on?
Why don't you just read the, as long as I'm full screen, I guess I can.
Okay, that's fine. Jeff Cole had one. Will the DSI study shed light on all of this?
The which study?
As the DESI study?
Oh, DESI, yeah. Well, that was actually the last contradiction. So that contradiction from the so-called dark energy survey, and that's again interesting propaganda. They're not surveying dark energy, they're actually surveying real galaxies and deriving mathematically conclusions about dark energy and dark matter. But they have found that matter is more concentrated than the theory predicts. Now, this is actually sort of almost icing on the cake, because this is not a huge contradiction. This is about a 1 in 20 chance that this could be caused by random variation. But it's of concern because it's on top of all of these other contradictions. So it's again the question, the theory isn't getting anything right. There are no recent data sets that they can point to other than the deuterium, where they can say, we made these precise predictions and they're precisely right. In the case of the DESI survey, in the case of everything else that's come out over the last 5 years, predictions are precise, but they're precisely wrong.
I had a question from David Paris. Please explain how the size of point light stars is calculated.
I couldn't get the end of that sentence, sorry.
Please explain how the size of point stars is calculated.
Okay, well, stars are too small to use as the source of this surface brightness test. We're using the size of entire galaxies. So galaxies are so big that even if there are extreme redshifts, up to redshifts are 8 or 9, so many billions of light years away from us, our best telescopes, like the Hubble telescope, can still resolve the largest of them. So in our study, we simply took the brightest galaxies, which are the largest galaxies, and we made a study of them. So there you can make they're very easy to measure because they have, especially spiral galaxies. Spiral galaxies have this interesting characteristic that their light falls off exponentially. So if you plot it as a logarithm, it's a straight line fall off. So you can measure their diameters very precisely, and that's how you get it. Stars would not be, only a few stars can we measure their diameters, so that would not be a good test. But with galaxies, we can measure them pretty easily. So what happens if we get rid of the hypothesis of the Big Bang? What happens then? Well, the first thing that happens is we can eliminate these imaginary entities that the Big Bang now requires that have no experimental or observational validity in the laboratory. We can get rid of inflation, we can get rid of dark matter, we can get rid of dark energy. And I have to agree with Joseph Conrad that if the universe were really composed of 99% dark entities that we don't understand, it would have been too dark altogether. Instead, without the Big Bang, with one exception, we can say that the basic processes in cosmic evolution are controlled by processes that we have observed and can understand on the basis of laboratory experiments and our observations in the solar system with our experimental devices traveling throughout the solar system. These processes basically come from electromagnetism in plasmas. Plasmas are gases in which electrons can travel freely. And the vast majority of the universe we observe are plasmas. Stars are plasmas, and the space between stars are filled with plasmas. So I'll get into these effects presently because I don't expect people to be familiar with them. In addition to electromagnetism, we have, of course, gravitation, and we have nuclear reactions, especially fusion reactions. So let's look at these principles and see how we can understand cosmic evolution. Now, of course, cosmic evolution from when? From the beginning? Well, if there was no Big Bang, there was no beginning. We have to instead start from the farthest back we can look. And this takes another viewpoint to how we describe the universe. As Hannes Alfvén wrote, to try to write a grand cosmical drama leads necessarily to myth. To try to let knowledge substitute ignorance in increasingly large regions of space and time is science. That means what we do is we look farther and farther out into space, farther and farther back into time. So when we start a story, it's not starting at some mythical beginning of the universe, which there is no such thing. It's simply the earliest time we can look at with our present knowledge. With our present knowledge, we can look back to a time in which the universe, with basically the same density of matter that we have today, the same energy density that we have today, was relatively homogeneous plasma. And we know one phenomena that had to exist in this plasma, and that is the pinch effect. Pinch effect is a very basic effect that was discovered by Ampere 2 centuries ago. And it basically says that if you have two currents moving in the same direction, they create magnetic fields which draw those currents together. If the currents are moving in the opposite direction, the same process pushes those currents apart. So if you imagine any plasma today or in the past in which you have tiny random currents, those currents will slowly grow because the currents that happen randomly to be moving in the same direction will pull together to form larger currents, and they will repel the currents moving in the opposite direction. So you will build up over large periods of time, and now we're talking trillions of years, from tiny currents, cosmologically significant currents. The second thing we know for certain about the situation in such a plasma or in any such plasmas is that the conductivity, the ability of electricity to travel through these plasmas is anisotropic. It's much easier along the magnetic fields than across. It's a little complicated to explain, but it's very fundamental. Because of how magnetic forces work, any charged particle circles around the direction of the magnetic field. Now, if we connect the directions of the magnetic field, which is a real thing in the world, we get an imaginary line called the magnetic field line. So it appears these electrons are circulating around the magnetic field lines. If the magnetic field is sufficiently strong and the plasma is sufficiently dilute, less dense, then the time it takes to circle around is going to be very small compared with the time it takes for one particle to run into another particle and collide. It's only through these collisions that a particle can move across the magnetic field and move to another field line. So that means it's much easier for currents to travel along the magnetic field lines, and in the end, currents only move parallel to the magnetic field. Well, as a consequence of this, and there's a straight electromagnetism, the basic way currents have to move through the universe is in force-free plasma vortex filaments. This was discovered many decades ago. So a force-free magnetic filament means that you have a filament in which the currents move straight along the axis, but at the outside of the filament, they're moving perpendicular to the axis. And in between, they're moving in helices that get looser and looser as they approach the axis. And if you do the mathematics, you find that that means the magnetic fields produced by the currents at each point lie in the same direction of the current. So this is a basic secret of the universe, that the universe is built up out of mainly plasma vortex filaments. This isn't the universe according to Eric Lerner, or even the universe according to Alfvén, who was the first, together with his colleague, Dr. Feldhammer, to point the importance of these vortex filaments. This is something that must occur if Maxwell's laws are correct. So this is the universe according to Maxwell. And if Maxwell's wrong, the light shouldn't be on. So we know Maxwell was right. The Veil Nebula is an excellent example in the present day universe of what these vortex filaments look like. This is a Hubble photograph with enhanced colors of the Veil Nebula. And it shows a hierarchical or fractal vortex filament. So you see the current lines, the plasma arrayed in a helical filament around the outside, the currents moving straight lines along the axis of the filament. And if you look closely at all of these subfilaments, they have the same structure. They have the helical structure and the straight structure, the same as the overall filament. Now, as these vortex filaments built up, they must have been affected by gravity. Gravity does not scale the same way electromagnetism. It has greater and greater effects at larger and larger scales. We see this, of course, gravity between ourselves is insignificant. It takes large objects like the Earth to have significant gravity. Once gravity started to affect these vortex filaments, they started to contract along their axis. Now, they didn't contract very much across their axis because these vortex filaments are spinning. And of course, there's conservation of angular momentum. So an object that contracts spins faster. And eventually that spin counteracts gravitation and prevents contraction across the axis. So you ended up with disk-like formations. And then you had a new electromagnetic phenomena, which is the homopolar generator process, also known as the Faraday disk generator, after Faraday, who discovered it. If you have a conducting disk moving in a perpendicular magnetic field, there is generated a potential between the outside and the inside of the disk, a voltage which accelerates a current between the outside and inside of the disk. So what that adds up to is the production in these primordial vortexes, a larger filamentary current of smaller sets of perpendicular filamentary currents. So you get perpendicular filamentary currents. All of this was hypothesized by Alfvén basically 40 years ago and was developed in part by collaborators, including myself. You get these perpendicular filamentary currents that can conduct angular momentum to the external plasma and subtract angular momentum from the contracting disk. So because these filaments can push the plasma very effectively, on the outside, the angular momentum of the disk decreases and you can get much larger gravitational contraction. So this sets up a hierarchy of smaller and smaller units. Back 30 years ago, one of my colleagues, Tony Peratt, a student of Alfvén, used a supercomputer to trace this process on the scale of a galaxy. And he shows in this filaments can push the plasma very effectively. On the outside, the angular momentum of the disk decreases and you can get much larger gravitational contraction. So this sets up a hierarchy of smaller and smaller units. Back 30 years ago, one of my colleagues, Tony Peratt, a student of Alfvén, used a supercomputer to trace this process on the scale of a galaxy. And he shows in this supercomputer simulation how two blobs of plasma can rapidly accelerate each other into the characteristic plasma shape of a spiral galaxy. And if you viewed this at a slower rate, you would see that these spiral arms are actually filaments themselves that are rotating. We see with 30 years of experimental and observational data, we see this hierarchy of filaments in quantitative detail formed at all scales. This is a image from ALMA of filamentary structure at the level of 0.05 light years. These are star-forming clouds that are all filamentary in structure and have the same strong magnetic fields, half light year. And if we go all the way up in scale, we see plotted 5 million light year radius. So this little radius across these red lines is 5 million light years. And these are hundreds of millions of light years long filaments formed of galaxies. So these are the evidence for these primordial vortices in the structure of the present day universe. Now, I said that this happens if there's strong enough magnetic fields relative to the density and temperature of the plasmas. Well, people have made observations of plasmas at the scale of intergalactic medium, clusters of galaxies, molecular clouds, and even protostellar disks out of which stars like our sun condense. And at all those scales, the magnetization ratio is orders of magnitude more than unity. And that means that these phenomena must work as we have described in a very anisotropic, very inhomogeneous way. The exception is when you get down to the scale of stars. Stars are sufficiently dense that collisions happen more rapidly than the orbits around magnetic field lines. So stars don't break up into smaller objects and are governed by different processes, including, of course, the process of thermonuclear fusion. which produces the energy that drives further evolution. Back 30 years ago, and more recently, I showed that from basic plasma principles, you can derive the basic quantitative size and scale of various objects in the universe. I don't have time to go into this, but this plots evolution of galaxies, plotting the density times the radius versus the density times the radius squared. And in summary, what it shows is that clusters, galaxies, and stars must evolve with the scales that are actually observed, which is these boxes up here, simply based on basic plasma theory combined with the laws of gravitation. From this basic plasma formation of structure, you can derive a model for the formation of stars in a galaxy. Back in 1989, that's what I did. And again, just briefly summarizing, this involves the production of very large supernova-producing stars only in a thin disk. Most stars in a forming galaxy form in a large halo, where stars that are between 12 and 4 times the mass of the sun burn hydrogen to helium very rapidly. So this model predicts the correct amount of helium and the correct amount of deuterium and lithium produced by cosmic rays produced in forming galaxies. So obviously, even though the universe had no beginning, every object within the universe did have a beginning. Galaxies had beginnings, stars had beginnings. So what we found is that you can produce not only structures, but the right amount of light elements. And when I updated this last year, and I'm still trying to get these results published, but I presented them at the American Astronomical Society meeting right before the pandemic, we can see that both the earlier and the updated version of this model produce the correct amounts of deuterium, helium, lithium, and 2 other elements, beryllium and boron, that everyone agrees are produced by cosmic rays originating from stars. Another big observation that confirms this theory is when we can look at galaxies that are forming. We can see them in the present day universe, or we look out into the distant universe and see how they were billions of years ago. These are called ultraluminous infrared galaxies because they're very bright. And just as was predicted, we find that relative to their mass, they're producing something like 100 to 200 times as much helium per unit time as is being produced by our own sun. So that produces in a period of 100 or 200 million years, while these galaxies are forming, all of the helium that we now see. And it also explains why in stars formed earlier in this period, the helium is not as much as those formed at the end. Well, this gets into the cosmic microwave background. It's been known for decades that if you calculate the energy that must have been produced by changing the observed amount of hydrogen into the observed amount of helium, you get the energy in the cosmic microwave background. Turns out that's about 4 million electron volts per proton. We know, because we can observe it, that this energy is being thermalized to dust within these baby galaxies. Baby in the sense of young galaxies. So they're very dusty galaxies, and the energy is thermalized down to 20 K. Well, but how does it get thermalized and spread out throughout the entire sky? Well, I and others developed theories of this based on what happens in the center of galaxies. In the center of galaxies, we have converging electric currents. Those currents we know from laboratory experiments, and I'll get into that in a minute, form twisted little bundles of vortex filaments, which have been named plasmoids. And these plasmoids have additional instabilities, which we've studied in the lab, which produce concentrated beams of ions moving in one direction and electrons in the other direction. So this is an artist's conception of the plasmoid in our lab, producing a beam of electrons and ions, which we observe. And this is observations by the ALMA telescope of M87 galaxy producing a beam which is viewed so that the magnetic field direction is shown by these stripes and shows that it is a current, an enormous electric current that's confined by its own magnetic field. Well, as we said earlier, this vortex filaments form a hierarchy of smaller and smaller filaments. And we know again from electromagnetism that these very tiny filaments, tiny in astronomical terms, can absorb and re-emit microwave frequency radiation. So you basically have a radio fog of these tiny filaments that are taking microwave radiation originally emitted from stars and from these clouds around galaxies and scattering it across the entire sky. What we're observing when we look at the microwave background is a radio fog, not the supercooled remnants of the Big Bang. Well, what's the evidence for this? The biggest evidence is that the universe is not transparent at microwave wavelengths. So astronomers know that there is a close correlation between the IR, infrared luminosity of galaxies, and their radio luminosity. But what I found starting 30 years ago, and I've updated it recently, is that, and this was published in Astrophysical Journal originally, as you move away from Earth, as the distance from our position increases, this correlation shifts. So this plots the radio luminosity at constant IR luminosity versus the log of distance from Earth. And that radio luminosity drops by over an order of magnitude, correlated with distance from Earth. Now that's totally impossible unless the universe is not transparent. It's transparent in IR luminosity, in IR frequencies, but it's not transparent in microwave frequencies. So this is direct evidence that we are living in a microwave fog. And I can go into the question period, but we've also seen direct evidence of observation of some of these tiny filaments. So to summarize, all cosmic processes can explain with lab-tested physics, except the Hubble process. The Hubble process is the one thing where we too, without the Big Bang, have to hypothesize that a presently unknown process is causing photons to lose energy with distance. There's no known plasma process that could cause this. But this doesn't have to be like dark energy. We can study this in our solar system with the technology we now have. We could put up satellites that could measure at distances of millions of kilometers a redshift and measure how that redshift changes with distance. And that redshift, if it was due to the Doppler expansion, would not be present in the solar system at all. So that's the one thing I would say we don't have explained. Well, finally, what does this all have to do with us right now? What difference does it make whether the Big Bang happened or not? Well, I think there's three big ways it influences us here on Earth. Obviously, right now in 2021, humanity is in a crisis. This is the most serious crisis we've faced since the Second World War, and basically in the lifetimes of almost all of us present here today. If you think that this is just a blip caused by the pandemic, I think this graph is a good way to see this is the outcome of decades of growing problems. The blue line charts the rate of annual decline in the mortality of human beings. So that peaked in the 60s. That was the fastest rate of decline of mortality. So the fastest rise in living standards. And that curve has been on a long downward slope towards growing stagnation. It's a little blip during the 21st century as China was integrated into a world economy. And of course, in the past 2 years has turned negative. The rate of mortality has been increasing. The red line shows the rate of energy increase corrected for the population growth. And again, this peaks in the 50s and the 60s and declines more or less in tandem. So what we have is a growing stagnation, a decrease in the development of the society over a long period of time, culminating now in a crisis in which standards of living are declining. Ending this crisis requires many things, but one thing it requires is energy. We need more energy, cheaper energy, so that we are not drawing vital resources away from healthcare and other things that we need to maintain the health of humanity. We need cleaner energy so we are not polluting the skies and weakening our lungs to make them more vulnerable to viruses like COVID. That means higher energy density, more energy out of less fuel. And the only thing that fits the bill is fusion energy. And if you're not convinced of that, please see our LPP fusion videos that I've highlighted at the bottom of this slide. What's the connection between fusion energy on Earth and cosmic evolution? To use the power that drives the universe, which is fusion energy, we need to understand those same processes that drive cosmic evolution. The pinch effect, anisotropic conductance, filament formation, plasmoid formation. Those are the key effects we need to understand to get fusion energy. For the tokamak device, which is the dominant device that most money is being put into, filaments lead to disruption. And they're pretty much impossible to control. So this is a great photograph of plasma inside a tokamak showing the filaments, and this big filament is disrupting the plasma. However, there are other devices, such as the plasma focus device that LPP fusion works with, in which we use the filaments to actually produce fusion. So in this little, in this device, we dump a lot of electricity into a very small place in a very short time. And this is what happens. First, these filaments form through the pinch effect, and they project themselves down our anode. And these objects are only centimeters across. By the magnetic field and the electric currents interacting. When they get to the end of the anode, they funnel into a hole in the anode, and the pinch effect pinches them together into a single filament, much hotter and much denser than what we start with. The kink instability pinches them horizontally or along the lines into a plasmoid. And thanks to Toroff Greek for this excellent animation showing the physical processes. This plasmoid, through its own instabilities, heats up to the point where fusion reactions start to take place. And through the instability I mentioned earlier, enormous electric fields are produced in the center, which accelerate beams of ions and electrons, which take the energy out. That means we can actually collect this energy, which is moving electricity, directly without putting it through the expensive process of boiling water and producing steam and running turbines. This is not just theoretical. We have seen these filaments and photographed them. This is an ICCD 0.5 nanosecond exposure of filaments going up the side of our device. You can see these 100 micron radius filaments. And then on the right, you can see a 200 micron radius plasmoid, which we have photographed in our device. And we produce these plasmoids in most shots. Because we are using these cosmic processes rather than trying to fight them, we actually have obtained better results by a factor of 1,000 than any private fusion effort. And we are almost up to the level of the biggest government effort, which is the JET tokamak, even though we've only spent 8 million and they've spent about 1,000 times as much. We are using PB11 fuel, which is going to be safe, no radioactive waste, compact, cheap, and decentralized. And the fuel, if necessary, could be obtained from seawater. I'm about to wind up, but the second way, important way that we need to end the crisis is we must win humanity as a whole to rationality, to the scientific method. I don't think that really needs reinforcement. But as Alfvén pointed out decades ago, one of the worst aspects of the Big Bang theory is to make science look like science fiction. Science became increasingly presented as the negation of common sense. The limit between pseudoscience and science tended to be erased. And it was difficult to find any difference between science and science fiction. So this is the sort of wow, gee whiz, that we don't understand dark energy, we don't understand dark matter, we don't understand inflation, but this is what's running the universe. This is the confusion of science with mysticism. If we abandon Big Bang, we can say the universe can be understood in a common sense way using the same technological and scientific concepts that we use to run our basic technology here on Earth. So scientific credibility doesn't become a matter of whether you trust scientists, but whether you trust rationality. And finally, in such a crisis, as much as we need energy, we need hope that we can escape from this crisis. Cosmic evolution, understood without the Big Bang, is running up, not down. If we look at the flows of energy in these various scales, we see that the flow of energy has increased over cosmic time and increased at an increasing rate. If we projected the evolution of life on this chart, we would see the same tendency. Unlike the Big Bang universe, which is sort of expiring from an enormous bang at the beginning to a petering out over time, the non-Big Bang universe is running up, not down. It is a universe that gives us rational reason to hope. So that's where I would like to end. Thank you very much for your attention for a long presentation.
Accelerating advanced fusion energy.